Hello, my name is Muskan Sarvesh, a PhD student at the University of Calgary. Today, I'll be presenting our work, Extended Reality and Digital Twin in the Oil and Gas Pipeline Industry, a systematic review on application, trends, and future directions. Over the last decade, the oil and gas pipeline industry faced challenges in construction, monitoring, and resource management. To address these, we propose using extended reality XR and digital twins DTs, which can greatly enhance training, safety, and system integrity, transforming how industry operates. Our related work spans several key areas in the oil and gas sector. We start with smart field technologies to improve data collection and automation, then building information modeling in oil and gas to streamline design and construction. We also looked at visualization tools and application in other heavy industries like manufacturing. Lastly, digital twins to transform operations in other areas of the oil and gas sector. We realized that although there are plenty of applications of DTs in the oil and gas industry, there is a lack of XR and DT integration in this domain. This paper aims to fill that gap by exploring their transformative impact in this sector. Our research focuses on three key questions. First, how are XR and TT technologies integrated into existing workflows and data management systems in the oil and gas pipeline industry? Second, what are the advantages and potential benefits of using XR and TT technologies in different oil and gas pipeline application scenarios? And finally, what are the trends or research outcomes that have been found or will be adapted in the near future to enhance efficiency in the oil and gas pipeline industry? Next, let's talk about the methodology. For our systematic review, we used the PRISMA method to gather keyword-based literature, yielding over 2,000 initial records. After removing errors and duplicates, three authors screened the titles and abstracts, narrowing it down to 56 relevant records. After separating 10 literature reviews, we categorized the remaining 46 papers by scenario types for detailed analysis. In this presentation, we will focus on the first five classification categories that are scenarios, data collection methods, technology, experience evaluation, and hardware used. For more details on all categories, please refer to our paper. Let's review the high-level results from our classification analysis. We chose monitoring, training, maintenance, and testing as four scenario types. Monitoring focuses on real-time data visualization and situational awareness. Training supports workforce drills and safety simulations. Maintenance ensures equipment reliability, while testing evaluates equipment performance to identify functionality issues. These scenarios highlight a variety of use cases that demonstrate the impact of XR and DT in the industry. We focused on three data collection methods: real-time, using live sensors, pre-recorded, mostly through historical datasets, and mock-up or simulated data collected using modeling techniques. Since a significant number of papers emphasize monitoring, there is a crucial need for real-time data collection. This ensures timely responses and accurate decision-making. We chose four technology domains: virtual reality for immersive environments, augmented reality that overlays digital information onto real world, mixed reality, which enables interactions in augmented and virtual environments, and digital twins as digital replicas of physical systems. Notably, the limited MR applications shows a lack of physical virtual interactions, highlighting a need for further exploration. Another category that we explored is experience evaluation, which focuses on human factors like user satisfaction, performance, and usability in XR and DT applications. As the graph shows, there is a significant lack of user studies, indicating a gap in research. The last category that I would like to discuss is the four hardware platforms used. We examined PCs, head-mounted displays, smartphones, and tablets. PCs are the most commonly used due to their strong processing power. However, there is a lack of use of wearable and portable devices like head-mounted displays, smartphones, and tablets, indicating a gap in the adoption of more mobile and accessible solutions. For our detailed review, we chose to dive deeper into the scenario category, focusing on monitoring, training, maintenance, and testing. In monitoring applications, we saw Lee et al. Demonstrate how integrating mixed reality with full-cycle digital twin systems in underground pipelines enhances spatial interaction, enabling intuitive visualization. Building on this, Staliandis et al. Developed a location-based augmented reality assistive system using GIS and global navigation satellite systems, specifically designed to manage underground utilities. Together, these examples illustrate how these technologies provide real-time data visualization, predictive analysis, and improved decision-making. In training applications, Andalus et al. Developed a VR solution to train operators in oil camps on different pipe scraping scenarios. Similarly, Santos et al. Created realistic simulations of oil platform training in VR to improve operators' understanding of hazardous environments and device locations. The takeaway here is that these technologies create an engaging, efficient, and effective training experience through data synchronization. In maintenance applications, Scarlett all used augmented reality for on-site visualizations to improve surveying and planning workflows, enhancing the efficiency of underground pipeline inspections. Similarly, Hertel et al. Developed an augmented reality prototype for gas pressure regulation stations, featuring expanding 3D models and digitized inspection form to identify requirements, challenges, and improvements. These examples illustrate how extended reality and digital twins offer continuous feedback and optimization strategies for safe operations in maintenance applications. Lastly, in testing applications, Lee et al. Used augmented reality digital twin systems with Boolean fiber optic sensors to assess and predict underground pipeline safety through an augmented reality interface. Similarly, Priyanka et al. Used digital twins combined with machine learning and prognostic algorithms to predict risk rates in oil pipelines, enabling timely failure detection and control through wireless communication. These innovations enhance situational awareness, visualization, and real-time guidance using data transmission and fault diagnosis. Through our systematic literature review, we attempted to answer three main research questions. First, we explored how extended reality and digital twins integrate into oil and gas workflows, identifying various use cases in monitoring, training, maintenance, and real-time modeling to enhance insights. Second, we examined the advantages of these technologies to improve accessibility to remote and hazardous environments, promoting safe training and supporting remote operations. Finally, we explored trends and future directions, noting that novel sensors and AI integration boosts predictive maintenance and operational workflows. However, these findings have also revealed several research gaps: a lack of physical virtual interaction, insufficient human research, and the limited use of wearable and portable devices. As XR researchers, they recognize that scaling these technologies will require better workflow integration and alignment with industry needs to truly maximize their potential. Thank you for patiently listening to our work. I'd be happy to answer any questions you may have now.